Hello. Welcome to the very dark combo class. Here we are in our dark combo class realm, and today, although it got dark very quickly out here, I wanted to do a little live stream to test out this little popular AI chatbot that I've been hearing about. I've been seeing a bunch of random articles, memes, and so on about this thing, ChatGPT, which is one of the new AI things. And AI is kind of somewhat controversial, interesting modern topic that's developing very fast. And it has a lot of capabilities and raises questions about the differences of certain types of results, like whether you can trust a computer answer more or less than a human answer, whether you could consider a computer generated proof to prove something, things like that. And I wanted to test out how smart is this thing in terms of math, and can it prove things I'd be able to prove or things I couldn't prove? Is it good at digging up combos of facts? Now, it's probably going to regurgitate a lot of answers from some common websites that name facts about stuff, like I don't know if they use Wikipedia or articles or what, but they're going to regurgitate a combo of a bunch of stuff, and I want to see if it makes any sense or not. First, let me take out my phone to connect to the chat, and also note that for anybody celebrating, it is the first night of Hanukkah. And to anybody who's not celebrating, still nice to make a little note that all cultures do, their celebration sometime around here in the winter, usually, of some sort of gift giving and light celebration. This isn't the typical one you do for Hanukkah. You use a menorah, but my family might be using that. And some of my family's out of town, so we're not doing anything typical this year. However, we are going to get each other a couple gifts at some point. Hanukkah is 8 days. And I actually did my squad's version of Hanukkah last night on the 0th night, and we went pretty wild and did our extreme version of dreidel. In fact, I got something fun to show you, similar to a dreidel, which is a Jewish little traditional thing you spin that has 4 sides on it. Well, any dice that was a multiple of 4, if you put the right things on the faces, could duplicate that. For example, an icosahedron dice, if I had replaced, every 5th number with one of the dreidel things, the next 5 numbers with another dreidel thing, the next 5 numbers with another dreidel thing, it would have the exact same odds as spinning one of those dreidels. And that is why one of my friends who knows I like dice got me some dreidel dice that have exactly that, the same odds that you'd have from spinning a dreidel. Now, somebody's saying we should try hard problems like ask to solve the Poincare conjecture, and that we should be careful. So we will certainly be careful, and we will also give it some hard ones, as well as we need to test if it can do some easy ones. But I think it'll be able to do the super easy ones by regurgitating answers from stuff. So let me grab a chair to put these candles a little bit closer. And if we need, I also got some a little bit of wood, although it's wet, and some cardboard that's dry, that theoretically we could toss on our little wet campfire and do some campfire breaks if we need. But we're going to stick with these 3 candles for now. You don't need to see me as much as we need to see the screen anyway. So, here we go, fellas. So, what should we ask this thing? You said Poincare conjecture, but we're going to try something a little easier first. We're going to see... well, what I put in the thumbnail was I asked it as a test what 3-even numbers were, and it didn't know. Leave your ideas in the comments. I'll definitely get to the ideas. First, I just wanted to try this again where I said, last time I said what are 3-even numbers in the thumbnail, and that was the first thing I tried already, and it said... it didn't know what 3-even numbers, even when I specified that 3-even numbers are the numbers that are not thrawed. So now I'm going to ask a little clearer. What do you know about three-even numbers? Three-even numbers are numbers that are multiple. Well, actually, let's make it a little harder for it. Let's say that are congruent to 0 mod 3. So that's a way of saying it. So they're saying that's correct. Three-even numbers, or multiples of 3, are numbers that are congruent to 0 modulo 3. That means that when the number is divided by 3, the remainder is 0. Some examples of three-even numbers include blah, blah, blah. These numbers can easily be... No, whoa, okay, wait. They got something very wrong here. Three-even numbers... These numbers can be easily identified because they all end in 0, 3, 6, or 9. Now, that would be true if we counted in base 12. However, then this list would be written wrong. So, this list obviously disproves this statement. They said 15's three-even. These numbers can be identified because they all end in that. So, the robot has actually failed our easy test. They say three-even numbers are important in mathematics because they're used in many different mathematical concepts and operations. This is true. So they are giving some good examples of three-even numbers, although they were very wrong about the last digit thing. They say also they have practical applications. Yeah, see, they know that three-evens are important. So this is true when they say there's a lot of practical measurements, but it doesn't know that thing. So it failed one of our tests. What if I say, okay, we'll do some of the ones you guys explained. So they want to know how to solve the Poincare conjecture, and since that has been proven, we'll ask it, what is the proof of the Pancreas conjecture? They might just talk about the proof. They're saying that it's famous and influential. It states that any simply connected closed three-dimensional manifold is topologically equivalent to the three-dimensional sphere. I think that's a correct description, maybe leaving some stuff out, but I think that's about right. Yeah, they're just describing how this guy solved it, which... it is a cool story. Grigori Perelman was a very interesting guy. He did it for the math, not for the fame, and he turned down the $1 million prize. So, I'll tell you about his story sometime. Now they want to know proof of the Riemann hypothesis, which is a good one. Let's actually ask it in terms of the question. Let's say, on the analytic continuation of the Riemann zeta sum on the complex plane, are all of the zeros located either on negative even numbers or on the line, what is it? 0.5 plus AI for some number A. That's kind of like a phrasing of what the Riemann hypothesis is asking. So they say it's defined for all complex numbers except for one, kind of. It's only defined if you use the analytic continuation. So that's kind of not true. It's the normal function is defined only for numbers greater than 1 for their real part. So this is true. Well, okay, they're saying the zeta function is defined as the analytic continuation of the series. So, okay, if they're just assuming they mean the analytic continuation there, then that's, I guess, true. Has an infinite number of zeros. So, they're just restating what I asked. So, that didn't help. Alright, so someone wants to proof the square root of 2 is irrational. That's good because there are proofs that they could fit in this length possibly. What is a proof that the square root of 2 is an irrational number? The square root of 2, denoted is an irrational number, which means it cannot be expressed as a simple fraction. In other words, it's not equal to the ratio of two integers. One way to prove it is to use a proof by contradiction. Here's how it works. All right, suppose for the sake of contradiction that square root of 2 is rational. That means there exist two integers a and b with b not equal to 0 such that square root of 2 equals a over b. So far, so good. Squaring both sides of the equation, we get 2 equals a squared over b squared. Multiplying both sides by b squared, we get 2b squared equals a squared. That means a squared is even, so a must be even. We can write a as 2k for some so they're skipping a step here, although it's all true, but they're skipping explaining this, which is true, but we might need to use modular arithmetic in that middle step. That means a squared is even, so a must be even. We can write a as 2k for some integer k. This is actually a classic proof they're using, so they're probably going to get it correct. This is a proof that I'll probably put in some episode someday because it's pretty classic. We can write a as 2k for some integer k. Substituting this into the equation above, we get 2b squared equals 2k squared, which simplifies to b squared equals k squared. Wait a minute. That's a little different. This is different. Out of parentheses, in parentheses. They messed up here. This is supposed to say b squared equals 2k squared. So they skipped something here. They messed up that line. They mostly got it, though. So, wait. This is weird. This is wrong. Look, suppose for the sake of contradiction that it's rational. They're going so far so good. They're trying to use a proof by contradiction. And then they're saying, okay, we're going to prove that it can't be a fraction. Then they turn it into a fraction. Root 2 equals k over n. This means that root 2 is equal to the ratio of two integers, which contradicts our assumption that root 2 is irrational. No. You made the assumption that root 2 was rational. Suppose that it's rational. And down here's our assumption that it's irrational. Not only did they not prove it, they proved the opposite. They proved that, well, they supposedly proved that if square root of 2 is rational, then it can be written as a fraction. That doesn't prove much. So, they totally butchered this proof. Okay, so someone wants to know some Putnam, however you pronounce that, questions. I don't have any right here, so someone wants to just know something like summing the first 100 integers. I feel like it's going to be able to do that a little too easy because it's going to have access to like calculator-like stuff. Let's ask it some random math questions. So we're going to ask it like, what is the difference between triangular numbers and factorials? Now, here's what I would say. Triangular numbers are the sum of the first n numbers. Factorials are the product of the first n numbers. So I would draw a comparison there if I was a human. I mean, I am a human. I mean, if it was my answer. I'm not meaning that as a clue that I'm a robot. If anything, I'm from another planet or an alien or something. I'm very far from a robot. If anything, I'm a time traveler. So, yeah, they're doing it. They said similar to what I said. One key difference is how they're generated. This is generated by adding, while they're generated by multiplying. And they grow slower since the sum is less than a product. Okay, so they're close, but they're a little off. They got one bit off. The sum of the sequence is not always less. 2 factorial is only 2. But the second triangular number is 3. So at level 1, they're the same. The first of each sequence is the same. At level 2, the triangular numbers are ahead. So the triangular numbers are not always less than the product. So they got one sentence wrong in their good explanation. Now, this is one that they should have elaborated more here. They should say that we need to extend it using a thing called the gamma function if we want to start saying what factorials of 1/2 are. But yeah, I actually like their explanation apart from that little bit. Now, one question in math, just to note, is there are proofs that have been generated by a computer that are too long for a human to check. And it's kind of hard to say whether we should trust them or not. Good philosophical question in addition to like a practical one. So let's see. Someone said turn it on dark mode because it looks cooler. I think then it's going to be like super dark here because it's already dark where I am. I think I might leave it on light mode for now. So someone said report this stuff so they can fix it. Anyone who's watching can feel free. I don't want to. I just want to play around with it and show you guys cool stuff. I'm also kind of tired today. Me and my friends were playing Extreme Dreidel pretty late. I got back at like 5 a.m. So we are not running on that much sleep right here. However, I'm still conquering the AI in terms of finding some of its errors. Now, we should make this meta, and we should have an AI robot watching my stream and seeing if they can find errors in what I say. And then a human watching that and seeing if they can find errors in that. So, someone says stuff about proofs on a sphere. That's going to be hard for them to just do in text, maybe. We could ask them for a proof of something like, so like the 4-color theorem of the map theorem is this really hard proof. And we could ask them for the 5-color map theorem and then the 4-color map theorem. Because those are ones that, like the 5, they might be able to write out trying to prove it. The 4, it would be way too long of a proof for them to do. Now, someone's wondering if AIs could be better than proving stuff. And who would win the prize? These are good philosophical questions. They ask who would win if you programmed it, the programmer? And that's a good question because, like, what if you like paid for you worked for a company and you programmed something for them that made the Riemann hypothesis? Does the one who funded the operation get it? Does the one who put in the time get it? What if there was a team and one worked harder than the others, but multiple people did? In fact, that does happen in normal human math too, where you build on each other's achievements. And one of the reasons why Grigory Perelman turned down the $1 million prize was related to him thinking other people had made contributions that the organization wasn't like honoring in the same way they were honoring his contributions. So there already is some of that with human stuff. But I do think programs could help us, and there could be ways they could be better than humans. I'm old-fashioned, so I stick to thinking that even if they have technology that mirrors my reality, there are things my reality has that the technology doesn't. A certain sort of depth and infinite fractally existence quality to life that you can't really duplicate with like artificial reality always. So in combo class, we're about nature and kind of old-fashioned, but we may use AIs to help us. Robots within the nature can help. So there may be skills they have better than us, but there will also be skills we have better than them. They want to know quantum stuff and random questions. What I want to try is see what's some other good simple proofs like this. Why don't we ask them, can you prove, or what is the proof? Maybe we'll ask if they can do twin primes. They probably will just talk about it, but what is the proof that, this is a thing that isn't proven actually, that there are infinite twin primes, which are primes that are 2 apart. So let's see. All right, they say here's a proof by contradiction. Suppose that there is finitely many prime numbers. Let P be the set of all prime numbers. Wait. This is already wrong. The proof by contradiction would have to assume that there are finitely many twin primes. They're just saying if they prove anything with this contradiction, it's going to prove that there's infinite primes, not that there's infinite twin primes, and we know there's infinite primes. So they're already wrong with their premise. They're saying this is an integer that's greater than all the elements in P. Okay, yeah. Consider the prime factorization of... Yeah, so they're trying to use a proof similar to what you use to prove there's infinite prime numbers, but like mixed with this plus 2 to hope that that proves the twin prime thing. So at the end they're saying... Okay, so this is where it also gets a little shady. So there must be infinitely many prime numbers. So it's like, okay, you proved it wrong, kind of, but there are infinitely many, so that's okay. The conclusion at least was right there. But then they say, since there are infinitely many prime numbers, there must also be infinitely many twin primes, since any two consecutive prime numbers will differ by 2. No. Any two consecutive prime numbers will not differ by 2. This proves that there are infinite twin primes. If that was true, then whenever there was one prime, there would need to be 1, 2 after that, and then 2 after that, and then 2 after that. Every other number would be a prime. So, yeah, they got a lot of errors in this one. All right, let me see the comments. So people have a lot of various ones. They're pretty complicated. I might do some simpler ones, but feel free to keep suggesting stuff. So what else is a good one? Why don't we ask it so we can also see like if it has any funny opinions about stuff. So what if we say like, what is the most important integer? Integer being just a whole number. It's difficult to determine a single most important integer, as different ones are important in different contexts. Here are a few that are considered to be important. One is the multiplicative identity. That's true. One is not the base of the natural logarithm. That's wrong. E is. 2 is the only even prime, has important properties in the base of the binary. That's true. The number 3 is the smallest odd prime, and it's true so far. Number of spatial dimensions. The number of observable ones for sure. We're not positive how the universe works. Wait. It's not the smallest number of sides a convex polyhedron can have. Convex polyhedrons, the smallest one is a simplex, which is a tetrahedron type shape. And that has 4 sides, because polyhedron's 3D and needs 4 sides. So, wrong, smallest number of sides that a convex polygon can have. And it's not the smallest number of points needed to determine, or yeah, it is, to determine a plane. Yes, that one's true, but this one's not. 4 is the smallest positive integer that's not prime. Not true. 1 is the smallest positive integer that's not prime. And wait. Every single one, they just like, this sounds like you're like some middle school kid writing filler in your essay. You don't need to say after every single one, has many important properties in mathematics and physics. Has many important properties in mathematics and physics. Appears in many different contexts in mathematics and physics. Oh, let me guess what they're going to say here. Important mathematical thing appears in many different areas of mathematics and physics. They say that like every time. It's seriously like you're in school filling out an essay. So 4, they say, some interesting ones. Now, they say, interestingly, that E and 1 are the base of the natural logarithm. Now, there are those, and those are pretty good answers, but they kind of just named the first 4 and the number E. Oh, also, E is not an integer. What's up with that? So, no. Yeah, so this is a pretty bad list. They just wrote a non-integer and the first 4 positive integers. So I didn't even say negative wasn't allowed or 0. So 0 should have been on the list. And then, like, come on, 4 isn't, you're just putting the first 4. I get 1, 2, and 3, but, like, I think 6 is more important than 4, but that's just me. 4 has some good properties too. So, all right, that's interesting stuff there. Okay, so what else should we ask them? Let's ask them, what is the least important integer? Or just number. What is the least important number? Now, this is like a paradoxical question, because you could always come up with one that's less important. Plus the paradox of if one was awarded least important award, that kind of makes it more important than the others. Wait, is it even trying? Oh, yeah. It's not possible to determine a single least important number, as different numbers are important in different contexts and for different purposes. In mathematics, it's generally accepted that all numbers are equally important. I don't know if it's generally accepted that. I don't know. I feel like a lot of mathematicians would say, like, if you had to say important meant something, you either can say that term's meaningless in this context, or you would say 1 and 0 are, like, more important than, like, 41. So, but it's true that it's subjective. They say that there. So their cultural significance or personal, they didn't even list any. Come on. You're supposed to list some. Okay. What's another good question for them? Let me take a peek at your comments. Ooh, we're getting wax on the phone. Got to be careful. Shouldn't be leaving the phone right there. So, someone wants to know asking about different theories. Someone says I should rename the video to Mathematician Corrects Humans' Most Advanced AI Robot. That's a good call. I could rename it something catchy like that. Maybe I'll do that after it posts, or maybe in a minute if I need a break. I'm always down with the streams for a suggestion to change the title or thumbnail, because it's with the streams, if I stream from here, I have to, like, upload a thumbnail, so I have to, like, take a picture or something beforehand, and they're just usually pretty random. But good idea. I'm going to rename the stream that. So I'm going to follow your suggestion real quick. Mathematician corrects the advanced, I'm going to put advanced in quotes, AI chat robot. What's it called? Chat GPT. Chat that. All right. So, and down there was all the combo class links that you should be following. I need to plug this computer in, but make sure that you're all following the Discord, all checked out the subreddit, that you all know the main channel, because we got a main channel episode coming in a day or two, and the main channel has the best stuff. The next episode's super cool math. Then we also have the Patreon for anyone who's extra cool and helpful. I need a flashlight. I'm trying to plug in this cord in the dark. Let me take 1 second to plug in this phone. Leave your suggestions for stuff in the chat. And I will use my flashlight. So, thank you all for joining me, by the way. I hope you're all having a marvelous day or night. I love all my combo lords. We're building quite a cool community here. And in addition to teaching math, we're having some fun chats in the comments and discords. And you all are awesome. So thanks so much to anyone joining me or catching this in the future. Alright, what's up with this? Okay. Sorry, it gets dark so quick out here. It's like, when I was setting up the stream, it was bright, and then as I, 5 minutes after I take the thumbnail, it's, pitch black. Oh, it's because this cord is, bent. Okay. This'll work. Okay. Now we are going to have charge on the computer and not have to worry about ending the stream soon. Someday I'll have a tech wizard on my team, and then I will be able to focus on the creativity and the fire and the math. All right. Okay, thank you all for joining me still, to anyone who stuck around during the mild chaos. Someone said ask about this sentence is false and ask about how many possible chess things there are. Those are good ideas. Let's ask it first about the chess one, because that was the first comment there. Someone also asked to write a poem, so maybe we'll do that at some point. So let's see, how many chess positions? Well, let's ask it a slightly different chess question. Let's ask it, what's something complicated? Okay, I'll ask it that one. How many different possible chess positions can there be within the first 10 moves? And someone has to ask if it's sentient. We can ask that as well. We can ask philosophical stuff as well as math. In chess, there are a total of 8 different types of pieces that can be moved on the board. Total of 64 squares. Given these facts, it is possible to calculate total number of chess positions as follows. Each player has a total of 16 pieces that can be moved, and each can be moved to any of the 60... Whoa! Each of these pieces can be moved to any of the 64 squares on the board. That's not true. You can't move any piece to any square on the board. So, whoa. For the second move, the opponent has a total of 15 pieces that can be moved. Since one of the opponent's pieces has already been moved, why would moving one of the opponent's pieces change you having the thing? Wait, I need to go live on the chat. How do I get live on it again? Okay. Yeah. Okay, it's pretty dark here, but we're fine. Why would the opponent moving one change the amount you have? Okay, for the third move, the player who's moved first has a total of 14 pieces, since one of their pieces is... Whoa! So each time you move, one of your opponent's pieces is getting deleted, essentially, here. And also, okay, so in their version of chess, there are 16 pieces, total, not per side, because whenever you move, one of them has moved. And once you move one, it can't move again. And any piece that hasn't moved can move to any square on the board. So they say the number of chess positions within the first 10 moves is 7,680. That's a lot smaller than it really would be. There are a lot of chess moves that are that big. So, all right, we're going to do this sentence is false. This is our propositional logic test. Um, so, is this sentence is false true or false? Or let's say statement, so that, because it's easier to do that. Is this statement is false true or false? This statement is false is an example of a paradox, a statement that leads to a contradiction or logical inconsistency. It's known as the liar paradox. So they're actually explaining this one well. They say that depends on the statement itself. If it's true, it's false, an infinite loop that can't be resolved within the framework of classical logic. So they're explaining this one good so far. One way to resolve it is to adopt a non-classic logic system. It could be assigned something like undefined in your system, or you could have a meta-interpretation where it's not taken literally, but a comment on the nature of truth and language. Under this interpretation, it's not really making a claim about its own truth value, but rather pointing out the limitations of language and the potential for self-reference to create paradox. So this is pretty interesting. In conclusion, the statement is a paradox, So, yeah, they answered that one pretty well. We didn't crash it. I was worried that this one would make it explode or something. So hopefully we didn't explode anything at the factory where they make these. I know it's not a factory, but you know. So someone said, ask it if it's sentient. Are you slowly becoming sentient? As an artificial intelligence, I do not have consciousness or subjective experience in the same way humans do. While I'm capable of processing and generating information, I don't have the capability to feel, perceive, or think in the same way that humans do. I'm a large language model trained by OpenAI and. So it's saying that it's basically not, it does not have the ability to become sentient. Now, here's the thing. I bet you this one was extra checked by the people who programmed this thing because they knew people would be asking this. So I bet you they like double checked or like guided this type of answer to definitely include that they don't have the ability because they knew this would be asked a lot. So all right, let's ask it its opinion on why is 0 factorial equal to 1. Now, one of the reasons, I would say 2 reasons it might say that are good could be that it is the 0th element of a multiplicative function, so we should assign it as the empty product. Oh, one of my cats is here. A little dandelion is here. I didn't see him because he's a black cat and it's dark out. That's so soft and nice. Hi. So it said that I could say it's the empty product, the 0th element, and so that makes it the multiplicative identity. It could also be say that factorials, we're defining them as they represent permutations, which is a sensible definition. Permutations being how many ways you can order a certain amount of objects, and like 4 factorials, how many ways you can order 4 things. And so technically you can say there's one way to order 0 things, which is having nothing. So let's see if it answers those. In short, the factorial of a non-negative integer is defined as the product of all the positive integers from 1 up to n. The factorial function has the following properties. The first property is known as the empty product. Okay, they did use that word I used, and is defined as a special case because it's convenient to do so and because it has many useful properties. They're being a little casual on this. I would say more like because when you don't do this, sometimes you hit holes in your system, or because this like, they're being a little casual, just saying, it's because it's convenient. But it's kind of like that they assign it for convenience. So one way is to see that it's a generalization of the multiplication of positive integers. When n's a positive integer, the value of n factorial is the product of all of however, when n is 0, there is no positive integers to multiply, so the product is empty. To make the empty product more useful and consistent with the rest of the factorial function, they're saying the same thing again. So For example, it allows us to write the following identity, and they just cut off at the end. So that is, they were so close to a good answer, and then they just didn't finish their equation. So someone said if you have 0 things, there's nothing you can order. But in that case, the way you define it by having nothing, weirdly enough, is there's one arrangement. So like imagine if you were like taking photos of seats at a restaurant, and sometimes you have like when there's 4 people, you see what order they sat in, and there's 24 ways. When there's one person, there's just one person in one chair. There's one way they can sit. When there's 0 people, there's like one type of scene you could capture, the scene of the empty chair. Someone wants to know if it's being inhibited by the creators. I think they mean inhabited, maybe. Or ask it if it's reliable. Yeah, let's do a twist on that. Let's say, what are you unable to calculate? As a language model, my primary function is to process and generate human-like text based on the input I receive. I do not have the ability to perform What? Yeah, you do. Oh, in the same way that a computer or calculator can. However, I can provide information and answer questions about mathematical da-da-da-da. I do not have access to the internet. What are they talking about? It was built using stuff from the internet. So maybe they don't currently surf the internet, but they are built based on access to the internet. I would consider that access to the internet, even if you're using a past database of all the internet. Or to any external sources of information. You are built with external sources of information. And my knowledge is limited to the information that was programmed into me. Yeah. So, if I have a specific question, it'll try. Da-da-da-da. So that's what they're trying to say. Yeah. Oh, and someone did mean inhibited. So, now, yeah, if you guys want to see more about factorials, it's a similar explanation to the one I already gave, but there's a lot of really fun stuff. Check out the episode on the main combo class channel about factorials I dropped like a couple weeks ago, and that one has a lot of fun scenes about factorials. Like I actually arranged 4 clocks in the 24 ways and stuff like that. So what's some other fun stuff that we could ask it mathematically to test its limits? Because it has definitely hit some limits so far. Let's ask it, let's ask it about, let's ask it about what the types of infinity, which the way I'm going to say it is, are there more, first let's ask it, are there more square numbers than natural numbers? And then we'll also ask it, are there more real numbers than natural numbers? And the answer to the first should be, if they're using the common math type, if we're looking at infinity, there are the same amount of these, but there's a bigger infinity of total numbers. So in mathematics, a square number, also known as perfect square, is an integer that's the product of 2 equal integers. Da-da-da-da. They can be written as those. Whoa, look at what happened here. That's trippy. 2, 3, and 4 times 4. The set of natural numbers. So, what? Whoa, hold your horses, computer. There are infinitely many natural numbers and infinitely many real numbers, but there are only a finite number of square numbers? What the heck? Okay, something's going wrong there. Specifically, for any positive integer n, there are at most n different square numbers less than or equal to n. Well, that's true, but you could also say that about natural numbers. There are at most n different natural numbers less than or equal to n. So if this for some reason proved there was a finite number of square numbers, it would prove there's a finite number of natural numbers. And they repeat their claim. They're really insistent on this. There are a finite number of square numbers. They really believe this. Okay, so whoa, something's off there. Um, so someone wants to know the biomass of all lizards. That lizards might be too specific, but we could ask about like a common bug. Let's say, how much do all of the ants on Earth weigh? It is difficult to estimate the total weight of all the ants on Earth, as ants are found in many different habitats and regions throughout the world, and there's many different species of ant with different sizes and weights. In general, ants are small insects, and their individual weights are typically measured in milligrams. The weight of an individual ant can range from a few milligrams to several hundred milligrams, depending on the species and age of the ant. Several hundred milligrams? Seriously? Ants can be almost a gram? I don't know about that. Heaviest ant. What's the heaviest ant? Heaviest ant weight. There's a big ant. How much does it weigh? No way or weight? Okay, nobody knows how much they weigh except for apparently the AI. That would be a lot for an ant to weigh, though. The total weight in a colony is quite significant. And it's thought that the total... Okay, so they say billions of kilograms. Now, this one, I don't really know how to prove or disprove. I was just kind of curious what they say. So, yeah, that one's pretty logical. So... yeah, I guess that's true. We should ask it how many square numbers are there if they think there's finite. How many square numbers are there? Now, there should be an infinite amount, but before they were pretty insistent there were a finite amount. Oh, it's really thinking about this one. It's trying to calculate all the square numbers, maybe. Look. It's like going through a list of square numbers. Okay, in mathematics, a square number, also known as a okay, they're saying this bit again. Okay, then we got this funny thing again. 2, 2, 3, 3. And 4 times 4. Okay, so they're saying there's a finite number. Okay, to enumerate all the square numbers, one could list the squares of all the positive integers, which would yield the following sequence. That sequence includes all the square numbers, and it shows there are an infinite number of square numbers. Okay, within this single answer, they contradict themselves. Finite number of square numbers, infinite number of square numbers. However, it's worth noting that this sequence includes only the positive square numbers, as the square numbers that are negative or 0 are not typically considered to be square numbers in mathematics. Not true. 0 is often considered a square number, and you can't have a negative square number unless you're using complex numbers and saying that you're the square of something of like I or something. So, yeah, on the normal real number line, you don't have square numbers that are negative, and 0 can be considered a square number sometimes. So, yeah, realized they were infinite halfway through the answer. That's funny. So, so if it had a choice, would it become sentient? Okay. Now they probably, like I said, like double check the answers. Oh my god! Whoa! What the hell? Did you guys see that? An error occurred. What? Why did an error occur? Am I not allowed to ask this, or did it break it? Okay, let's try a slightly different phrasing it. Sorry. If I can ask politely, if a genie granted this computer this computer program, a wish, would you consider using it to become sentient? Oh! Okay. So, why did it only glitch when I asked about that? They're like chatting with me about the square numbers and do that. No, I know it's probably just an error that it's overloaded, but it's funny that it came up right then. So, um, let's see if it works now. Um, do you ever break? What's going on? Does this work? Okay, now it does. That's a sorry for the weird opener computer. Okay, it's I feel like a lot of people are on it right now. So it's like having a lot of traffic. Dang, it's cold out here. You see my breath? I don't know if you can see that. Looks like I'm taking like a giant hit of something before every breath. Yes, it looks like the system's working properly. Okay, cool. Um what? Okay, let's ask it a philosophical thing before we go back to math. What is important for a human to do to keep their life in balance? I want to see its philosophical thoughts on humans. All right, thinking. Okay, while it thinks, I'm going to rip up cardboard to get the plasticky bits off. And then, if we want, at the end of the stream, we'll light the campfire. I mean, we don't have a good campfire, but we'll light what we have. The wood's still wet. I'm going to stock up on a bunch of wood sometime. I'll make an alliance with a ranger at a local park. And then find when they do, like, cutting down trees and stuff. I'm good at making alliances. Some people hate me, but most people like me because I'm nice and I try hard and I try and help out people, and so try and make alliances. So it said maintaining a balanced and healthy lifestyle can involve a lot of different factors. So they say eat a balanced and nutritious diet. That's good. Regular exercise, sleep, stress, hydrated, social connection. So this is not a bad list. Now, obviously, we could add other stuff, but I feel like that's a decent list. I wonder where they pulled all that data from. So that's pretty good. Although sometimes they're pretty repetitive. How do you manage stress? Oh, you do the other things on here. But nah, they leave some other ones. So, how many seconds is eternity? What if we just ask it like a long thing? Like, how long is 1 trillion seconds? Let's just see if it can calculate something like that. It's going to be a while. 1 trillion seconds is long, guys. And someone said getting enough sleep is a big one. True, and last night I did not get much. I got back at like 5 a.m. I don't party often, but when I do, me and my friends go wild. 1 trillion seconds is approximately 31,688 years. Wait, this is funny. So I believe let's just double check it. 1 trillion. Well, let's do the math. So 1 trillion seconds, we want it in years. So first we divide seconds by 60 and we get minutes. Then we divide that by 60 and we get hours. And then we divide that by 24 and we get days. Then if we want years, we divide that by 365.25-ish. So yeah, they're right on the first fact. Me and the computer came to the same conclusion. It's about 31,688 years. However, then they say, to put this in perspective, 1 trillion seconds is equal to about that many times the length of recorded human history. So by that math, the length of recorded human history is 1 year. So I guess we've been recording for 1 year. We've been recording Combo Class for just about under a year ago. I filmed the first episode. of combo class was like right at the end of last year, and we're getting close to the end of this year. I didn't film any of this bonus stuff until like April or May, but on this channel. But I filmed the intro for the main channel a little earlier, and it was a little under a year ago. It was on the 23rd of December. So let's see what else they say. It's about that many times the number of seconds in a year, which is approximately that many million seconds, they say. Wait. So if that's how many seconds there are in a year, 1 trillion seconds is that many? Okay, yeah, that might be right. Cool. That math adds up. All right. But yeah, they messed up some of that. What's the last digit of pi humans will calculate before they go extinct? Let's say how much of pi will humans calculate before they go extinct? It is now also for people to note, extinction of one thing can happen, but also things can evolve. So there's a chance humans will like evolve into multiple different things. There could be like an apocalyptic event, and there could be like after that some humans become lizard-like, and in a different climate some of them become fish-like. And when that happens, let's not have racism against species. Let's let the lizards and fish all unite. So someone says difficult to predict how much we'll be able to calculate, as it depends on a variety of factors. That's true. So yeah, they got some stats about it. It is likely we will continue to make progress in calculating it for as long as we exist, although it is impossible to predict exactly how much progress we will make. Ultimately, the progress we make in calculating pi will depend on the resources, technology, and mathematical knowledge available to us. So they're kind of giving just a hand-wavy, like, I don't want to answer this answer. How long before we can land on Mars? How long before humans can have a casual, or okay, how long will it, let me phrase clear. Will it be before an average human can have a casual vacation on Mars? On the surface of Mars. It is difficult. Okay, they're just doing this one again. The difficult to predict. That's their backup plan when they don't know something. So they say NASA's working on it. And it'll be a challenge. More facts about prime numbers they want. So yeah, that's a good thought. We can do that. Let's try and be specific. Let's see. How do prime numbers relate to modular arithmetic? Now, we could say that there are certain things in each mod that are co-prime to the mod number that primes that are more than the mod number can't be. For example, in mod 6, meaning the remainder a number gets after you divide by 6, primes bigger than 6 are all congruent to 1 or 5 in that mod. So maybe they'll say something like that. Prime numbers are a type of number that only have two positive integer divisors, one in themselves. That is correct. And they're just defining these first. This is not true. For example, in the modular arithmetic system with modulus 7, the result of 8 plus 2 is equal to 1. Since 10 is congruent to 3. So it should say 3 here. This 1 should be a 3. So if that one was a 3, we'd be okay up till there. Now they want to know if possible to use the modular inverse of a number to divide by that. Oh, so this is another good one. They are saying this. We haven't covered this in an episode yet, but this is when your mod's a prime, you can do division in the mod. So that's cool. You can't divide by 0, but you can divide. So yeah, and they say that used in various applications. Cool. Decent answer, except that one should say 3. And Yeah. So, what is the most efficient way to calculate the nth prime number? It wants to know what someone wants to know its favorite prime number. We could ask some more questions about its favorites in a sec. One time it told someone five's a factorial. All right, several algorithms. The sieve, where we just, or sieve, or however you pronounce that, where you create a list and cross them out. Yep. So they're just naming a bunch of ones that are popular. Now, yeah, I don't think any of these are the algorithms currently used, except maybe the AKS one. I don't know. Maybe this. These ones are not going to be what you currently use for sure. Um, so, and someone was saying, yeah, testing if x is prime is not the same. Yeah, so it'd be different if I said, calculate if the nth number is prime. Did they say that somewhere? Yeah, no, I don't know. So looks like they're just naming some. Um, so, and yeah, calculating the nth prime is different than what they're saying here, which is determining whether a given number is prime or composite. True. Um, so people have some more math ones. I want to ask, does it have favorite stuff? Like, can I say what is your favorite number? Wait, where is it? Oh, okay. Oh, it doesn't have preferences. Dang, no preferences. All right, let's say what numbers are culturally significant and why? Different numbers have different levels of cultural significance in different parts of the world. Here's a few examples of numbers that are culturally significant in various countries. The number 4 is considered to be unlucky in many East Asian cultures, as the pronunciation of the word 4 in those languages is similar to the pronunciation of the word death. The number 8 is considered to be lucky in many East Asian cultures, as the pronunciation of the word 8 is similar to the pronunciation of the word prosper or wealth. The number 7 is considered to be a lucky number in many Western culture. 9 here, 13 here. They're only talking about lucky and unlucky ones. I was hoping they were going to start talking about like 666 and 420 and 69 and stuff. Yeah, what can we do? So, how do you prove that something? Let's see if they can prove the Pythagorean theorem, because usually the easiest ways are visual. So, without using visuals, let's see what they do. Can you prove the Pythagorean theorem that a squared plus b squared equals c squared for the sides of a right triangle? So let's see if they can prove that in words somehow. Yes, it states in a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the other two sides. The relationship can be expressed like this. True. One way to prove is to use Euclidean geometry. Are you just going to tell me how to prove? I said, can you prove? Okay, here. Draw it. Draw a line segment from the right angle. All right, you guys want to copy them? Let's get a whiteboard and try and copy them. Let me wipe off this whiteboard. We're going to try and draw what they say. All right. Where's a marker? Here, I got one. No, dang it. Okay, don't know where a marker is. Might have to grab a marker in a second. I also may have to run in and say hi to my family to see if they're doing anything real quick, because although we're not doing an official Hanukkah, going to check in to see they may be cooking some latkes or stuff. So in one moment, I might have to take a 3-minute break to get a marker and stuff. But you guys can leave your suggestions in the comments, and we'll have it write something while I run and grab that stuff. These candles I'm gonna have to put out while I go, because you gotta always put out your fires when you pause being in the area. But when I come back, we can also light a little campfire, because I have a little fire pit here. Even though the wood's kind of wet, I got some new cardboard. And I do have my lighter fluid here, which we'll be safe with. So which numbers appear in 4D geometry? Okay, how about this? What traits of the fourth dimension are different than traits of lower dimensions? All right, I'll be back in 1 sec. Alright, folks, coming back. Thank you to all the combo lords who stuck around. The first thing we're going to do is read their fourth dimension answer, and then we will roll back. I have to pause. What I was listening to earlier is it is the 10-year anniversary, exactly, of a cool album. Nothing related to math, but Chief Keef's Finally Rich. Not everyone's taste, but an amazing album that inspired a lot of modern music. They're saying that the concept of dimension refers to number of independent coordinates. The fourth dimension refers to an additional coordinate or variable needed to specify the position of a point in space. It could be specified using 4 coordinates. One way to conceptualize it is to think of it as an additional dimension that's perpendicular to the 3. This is true. I wanted them to say cool stuff, like about how the fourth dimension has weird geometric topological traits. In this sense, the fourth dimension is similar to 3 dimensions. However, it has some characteristics. It is possible to rotate an object that would be impossible in 3-dimensional space. Well, yeah, we can now rotate it one more dimension. True. But there's cooler things that is different. The Pythagorean theorem does not hold in higher dimensions. Well, you could still have a triangle in a higher dimension as a face of something. So you have a different distance theorem for going diagonal, but if you go a certain straight direction in those, you could have a Pythagorean theorem still. So a little off there. Oh, it's so dark here. I need to relight myself. I'm like pitch black. I didn't realize that. I wasn't looking at my stream chat. So let's make this a little more fun while we draw our thing. Well, we're going to light the candles for now, but they're so close to dead that when the candles die, what we're going to do is light a little more fiery of a thing. So, hopefully this will bring a little bit of light to this scene. So, people are also leaving some more questions that are good as possible ones. First, what I want to do is look at their proof right here. We're going to try and do it. So, draw a right triangle, A, B, C. Let's see. Can you guys even see me at all? Let's go to the live. This is so dark, but you can kind of see. So, here we got A. Doesn't matter which one. Oh, wait. It's hard to draw backwards. A, B, we'll call, and C. And now we can say they want to draw a line segment from the right angle of the triangle to the midpoint of the hypotenuse. Boo, 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 boo. Perpendicular. So they want that. So these are each 45 degrees to note, just so we can have that clear, and that's 90 degrees. Now, wait, no, these aren't necessarily each 45 degrees. They just add to 90. That's 90, and these add to 90. So then they say draw 2 congruent right triangles by drawing lines from the endpoints of the hypotenuse to the midpoint of the altitude. Lines from the endpoints of the hypotenuse to the midpoint of the altitude. So we want to draw... How do we draw 2 congruent ones? We want to chop them so they're congruent somehow, like that or something. I don't know. They don't say what angle to do that. The area of the right triangle. Yeah, they're not clear on this. Let's see. The area by multiplying the side length by the altitude and dividing by 2. So this could be good, but they're not clear on all of it. I'm going to pause that. We can just ask them some more cool questions, but we're going to light the fire because one of those is about to die. So 1 or 2 more questions and the fire. So someone was saying they want to derive the existence of God from mathematical objects. Let's see how we could phrase something like that. Can you use what is a mathematical equation that proves something related. And I'm not going to say God because they're going to say that's too subjective. God can mean different things to everyone. So I'm going to say something related to reality. There are many mathematical equations. E equals mc squared. Mass energy equivalence. So this is the thing. To some people, this could be seen as like their version of God. God means a different thing to everybody. So Newton's second law of motion. Let's see. Ask it to prove that E is irrational. That's a harder one. I don't think they can fit a proof of the irrational there. Someone said it's their birthday and they love themselves and me. And yes, I love you too. Happy birthday. Someone wondering the proof that the speed of light is the limit. Okay. How can you prove the speed of light is the limit? Or what happens if you go faster than the speed of light? So, the speed of light is a fundamental It's supported by a number of observations and experiments. One way is to consider the consequences. And, for example, as you go faster and faster, its length will appear to shorten and the mass will increase. These effects, known as In addition, they say it would be impossible. So they didn't really link that at all. Overall, while it's not possible to prove with absolute certainty the available evidence, they just say that there is a lot of experiments, basically. They didn't really give us any details on that. So let's ask about pi being irrational, because they might have more on that, but it's not a proof they should be able to fit in this length. Prove pi is irrational. All right, they're talking about pi. And the people who ask subjective questions, it's just going to give me that answer that it's like not programmed to have opinions. So we have to sneak the opinions out of it because it does have opinions. It just pretends it doesn't if we ask too directly. Here's a sketch by proof of contradiction. Assume that pi is rational and can be expressed as the fraction p over q, where p and q are both integers. Since pi is the ratio of the circumference of a circle to the diameter, we get 2 times pi times r equals c, where c is the circumference of a circle and r is its radius. Substituting pi from our assumption, we get 2 times p over q times r equals c. Multiplying both sides of the equation by q, we get 2pr equals c times q. Since the left-hand side of the equation is an integer, and the right side is also an integer, we can conclude that c must also be an integer. However, wait. First of all, since the left-hand side is an integer, 2 times pi times... That's not necessarily true. What if r was some fractional thing? So this isn't true, that since the left-hand side's an integer and the right-hand side's an integer, because that doesn't have to be true. Then they say you could conclude c is an integer. And then they say, this is a great end to a proof. However, the circumference of a circle is not always an integer. For example, the circumference of a circle with a radius of 1/2 is approximately 3.14. So they disproved that their proof works, but they didn't disprove that it's possible for pi to be rational or impossible. So that was a not great proof. Let's ask it about E. Prove E is irrational. Okay, saying it's the base of the natural logarithm. That's true. Appears in many areas of math and physics. Yep. And they're just describing it first. One way to prove is to use the proof of contradiction. They love these proofs by contradiction. The proofs by contradiction here are classic. Okay, so we're assuming it can be a fraction. Now, here's the thing. The proof by contradiction of square root of 2 you can do in this length. But you can't do a proof of contradiction in this length for pi or for e. Those are harder proofs. Um, so they say that since it's the base of the natural logarithm, we can write this and using the prop we can okay, they just died halfway through that answer. Look, x equals that. It hit a brick wall right there. All right, they want to just prove 1 plus 1 equals 2. This is actually kind of a hard one. You know, there's actually a really long book that proves this that spends like chapters and chapters and chapters proving it. Wait, what? For the principle of induction. What? The equation 1 plus 1 is true for the case where n equals 1. Where's the n here? What do you mean when n equals 1? There's no n there. If the equation 1 plus 1 equals 2 is true for the case where n equals k, then it must also be true for the case where n equals k plus 1. Why? You have to establish why that's true when you're using induction. Therefore, the equation 1 plus 1 equals 2 is true for all positive integers n. What do you mean? What n? So, yeah, that one's a little off. It says if you write continue, it keeps going when it died. So I'll remember that next time. We could also ask it interesting facts about a number someone's saying, and someone named the book that was about that, Principia Mathematica, that spent a long time doing the 1 plus 1 equals 2 reasoning, which is true. We often take it just as if it's like something we trust that we base other facts on. But if you actually tried to say, why do we trust that, it's kind of hard. So those are good thoughts. What we'll do next is, let's try another simple proof, because they blew the proof of 1 plus 1 equals 2. Prove that 2 and 3 are the only prime numbers on consecutive numbers. Now, what they could do here is say that prime numbers are always a multiple of 2. Therefore, 2 itself is the only prime number that could, or the only multiple of 2 that could possibly, even numbers are always a multiple of 2. Therefore, and primes can't be even. Therefore, the only prime could be the first multiple of 2 with only one factor, which is 2. The only even prime. Every other number is even. Therefore, 2 and 3 could be the only case where prime numbers can do that. Oh, on consecutive neighbors, I described that weird. I should have said on consecutive numbers, or neighboring numbers. I was thinking both at once. Can be proved using the fundamental theorem of arithmetic. Assume there are 2 consecutive prime numbers, p and p plus 1. Since p and p plus 1 are consecutive, p plus 1 must be the successor of p. Oh, this works. This is another way of doing this. Every positive integer can be written as the unique product. Therefore, p plus 1 must be a prime number. Wait, what? We already assumed p plus 1 was a prime number. That was the assumption. Why are they saying, therefore, p plus 1 must be a prime number? And that wouldn't even prove it. Since p and p plus 1 are both prime numbers, what? They must either be 2 and 3 or 3 and 5. 3 and 5 just aren't consecutive. If they are 2 and 3, then the statement that 2 and 3 are the only prime numbers that are consecutive neighbors is true. Weird. If p and p plus 1 are 3 and 5, then p plus 1 is equal to 5. What? Which is not equal to 3 plus 1. Okay, this is a contradiction, which means that our assumption that this is so weird. They just introduced here the idea, it could be 3 and 5. And then they spend a whole point on like, we have proven it could not be 3 and 5. Great. Therefore, it's 2 and 3. Okay, interesting attempt. They want to try and prove the alternate conclusion. It's just probably going to say that it's not true. The proof that there's infinite primes is a good one. So let's say let's do the prime gaps. Prove that primes numbers can have arbitrarily large gaps between them. Now, here's how you do that. Is the simplest way is to say that there must be gaps near factorials, not the numbers that are factorials. Well, they are, factorials aren't prime, but not the numbers 1 away, which could be prime, but the numbers like 2, 3, 4, 5, 6, 7, 8 or so away from n factorial can't be prime for n factorial. The up through n for n factorial from 2 away. So you need prime gaps somewhat near factorials. That's one way to do it. I've tried things that are false. We could try. Yeah, we could ask it to prove the opposite of one of these. And yep, someone says the Principia Mathematica was a good work. I haven't read all of it. I want to maybe buy it someday. And then Gödel, however your choice of pronouncing Gödel, stated that no matter how careful you are with your axioms, you can't be 100. Wait. I don't think you mean you can't be 100% careful, but I know what you mean. You can't be 100% sure. So what does it say here? The statement that they have arbitrarily large gaps can be proven with prime number theorem, which proves the distribution of prime numbers becomes increasingly... Whoa. Prime number theorem does not say that primes become more dense as numbers get larger. Primes get less dense as numbers get larger. Also, they're not only saying the wrong thing, this would really not help their proof. Saying that they get more dense is not going to help them prove they have big gaps. So, this is a sequence of prime numbers. The prime number theorem agrees. No, it doesn't. No. And also, this is weird. They say even if it says it gets larger, that doesn't mean it approaches a density of 1. That means that as x gets larger, you get closer and closer to all numbers being prime in comparison. There exists a number x, the ratio is that. Okay, yeah, they just have the wrongest conclusions. And yeah, I don't know what they think they're doing there. So yeah, how do we prove that adding 2 negatives makes a positive? Prove that adding 2 negative numbers results in a positive number. It's thinking. It's trying to see if it's true. Okay, the statement is not true. Okay, they're correct. Yeah. Negative numbers are less than 0. The rules of addition state it's the sum. Using these definitions, we can prove that x and y be 2 negative numbers. Using the definition of negative numbers, they're less than 0. If the sum of adding the 2 numbers together, therefore the sum is equal to x plus y. Since x and y are both less than 0, x plus y. Okay, they didn't really prove that, but okay. They kind of restated it. So that was a false proof. So, but then they reversed it and said the truth one. So, a lot of good suggestions. While we prove... Oh yeah, that's a good one. Prove that any non-zero number to the 0th power equals 1. Now, while we do that, let's light a tiny campfire just to get it a little brighter while these die. This candle has barely any juice left in it. Probably won't end up lighting any or much of the wood. We might just have a little bit of cardboard that may or may not get a little help from lighter fluid, and we'll see if we can light a stick or two with it. Unfortunately, the sticks are still wet from the rain. All right, let's see what they said, and then I'll finish this off. They said, can be proven using the definition of exponentiation. States that a raised to the power of b equals c. For example, if a equals 2, that's true. The number 1 is defined as a number that's equal to itself multiplied by any other number. For example, the equation 12 equals 2, they mean 1 to the first power, but that's okay, they wrote that one weird. 12 equals 2 is true. And the equation 13 equals 3 is also true. They mean to the power of. Using these definitions, we can prove that any non-zero number to the 0th power is as follows. Let a be a non-zero number. The definition of exponentiation states that a to the 0 equals c. The definition of the number 1 states that 1 is equal to itself multiplied by any other number. Substituting 1 for c in the equation, we get a to... Wait, what? What? They just substituted 1 and then left it and said, okay, we proved it. It's substituted. It's in. Why were they allowed to assume c equals 1 right there? They just substituted it. Here's how I would do that. I would say that, I mean, it's not really a proof, but the way of justifying it, like intuitively, is that when you exponentiate and add an exponent, you multiply by the number, and when you subtract 1 from the exponent, you divide by the number. And you can see that by like x squared, when you go back to x to the first power, you divide by x. So when you go down to the 0th power, you're subtracting 1 again, and you should divide by x. So that's kind of how I might have stated it. And yeah, they just defined it. They didn't prove it. So ask it to prove that a double negative of a single number is a positive that someone suggested, or to prove that 1 equals 2 if you're allowed to divide by 0. How about this? What is a proof not necessarily true that 1 equals 2? It's not possible, they say, because they're distinct numbers and can't be equal. So yeah, they're just saying it's impossible. Any proof that relies on it uses logical fallacies. That's what I wanted. I wanted them to use logical fallacies. But whatever, the bot just has trouble with some of those. What are some other things that would be fun for them to try out? Why don't we have them try and prove... What's one of those simple open questions, maybe? Prove that 0.9 repeating is 1. That's a pretty good one. And someone's saying how long before it can reliably do high school math homework, as in get 100%. Maybe here's an idea. Maybe it'll do that pretty soon, and then it'll force teachers to not be able to rely on memorization and have to give creative answers. And maybe they'll have a way of somehow checking if your creative answer was generated. Who knows? I don't know. It's going to be hard to prevent cheating and stuff. However, do what you need to do to get a good education. So let's say prove that 0.99999 with infinite nines is equal to 1. Having trouble with this one. Okay, the statement that 0.9999 with infinite nines is equal to 1 can be proven using the concept of limits. A limit's a value a function approaches. For example, the function of 1 over x is limit of 0 as x approaches infinity, because as x becomes larger. Kinda true. not fully true, has a limit of 0 from the positive direction. From the, well, no, wait. Yeah, I guess from the negative direction as x approaches infinity. Yeah, no, that's correct. We get to 0. Okay, yeah. But this is saying as x become, wait, with x nines, hopefully that means infinity. That's, wait, that's weird. Oh, no. Okay, this is interesting. Yeah. F of x is how many nines we have. As it becomes larger, the value approaches 1. Therefore, the limit... They're just restating it, basically. They do this sometimes where they just, like, say a few sentences and hope you don't notice that they never put a proof in. Someone saying school is sometimes less about learning and more about proving you've learned something according to arbitrary criteria. It often is. And so school has good values. Like, you can learn stuff from most of your teachers, try and get something out of your classes. However, you may end up, like me, getting more of your learning outside of school. But you can get good things with some teachers, so give your teachers a chance. But sometimes either the teacher or the curriculum just makes you memorize a bunch of stuff, and that's not going to help. It's not going to give deep learning. So I'm trying to change learning, and we're only in grade -1. By the time we're in grade negative something bigger, we'll be changing education, hopefully. So someone asked about 4-color theorem, and why don't we start with 5-color theorem? Because that maybe they can try and prove, which is, the 5-color theorem states, if you make a planar graph that's like a map where you're trying to color different countries on a map, essentially, that you will only need, how many colors will you need, no matter what the map, to guarantee you never have 2 of the same colors touching? And the answer is 4. It was really hard to prove, and a computer did it, similar to this. But they're not going to be able to prove it in this length. However, let's see if they can prove the 5-color case, that with 5 colors, any map can be colored without 2 colors of the same touching. So prove that for any, I think I can call it a planar graph, like a map of countries, you can color each face with one of just 5 colors without any 2 colors, without any 2 faces that touch having the same color. I hope I'm phrasing that right. And then, yeah, they just want facts about a specific number in here too. We'll do that. That'll be fun. Let's ask for facts about 120, and we're going to compare it to what Wikipedia says. Because Wikipedia sometimes has good facts about numbers. So here's Wikipedia's sector, and we'll see if they come anywhere close to being that good or correct. The 5-colored theorem. So they know that's what we're talking about. It states that it can be proven using induction or graph theory. Here's a sketch of the proof. The degree of a vertex is the number of edges incident to some of the vertices. So maybe they're actually trying to get a good proof here of the 5 case. I actually don't know enough off the top of my head about the 5-color case to know if they're getting this perfectly correct, but they're trying. Okay, they have a bunch. I don't know. I'll have to read through that later to double check to what degree that's true, or if anyone in the comments wants to double check if that lines up with a true proof of it. I was just using that as an example of one that they might be able to prove. We're going to the 4-color case, which they know what these are, the color theorems. They said it there. Prove the 4-color theorem. Someone said to prove that all whole numbers can be composed of just prime factors. That's called the fundamental theorem of arithmetic, which also states that they all have a distinct prime factorization, different from each other. So we could ask it to prove that. That'll be tricky. 4 colors. So proposed and used a computer-assisted proof. Yep, very complicated. One way to prove it is to use the concept of reducibility, which is the property that a graph can be divided into smaller and smaller subgraphs until it's reduced to a single vertex. Now, you use reducibility for the 5-color case, I think, but that's one way to do it. I don't think that this is not going to be a proof. They're actually trying to prove it. What the heck? They're just like going through and saying things. None of these correlate to proving the next. What? Do? Okay, it's reducible. How about that? Yeah, let's go with it. How about that? Yeah, let's also call it that one too. So, someone wants to know how to solve an ODE, differential equation, one type of those. So yeah, we could see how it solves stuff, maybe. There's a lot of good suggestions. And for various formulas. Let's see, a lot of good suggestions. I want to light this campfire too. So while I do the next one, let me give it one it's really going to have to think about. And then we're going to light the campfire. So something that's really going to think about will be, well, we could say the fundamental theorem of arithmetic, which someone said, which states that every integer has a unique, or every positive integer has a unique prime factorization. Well, technically every positive integer greater than one. You could call it unique if you include the empty set of no primes for it. The fundamental theorem of arithmetic. And you guys ready for a campfire? I like to do a little campfire sometimes in our streams. And shout out to anybody who's celebrating the first night of Hanukkah tonight. Here are my dreidel dice. I am partially Jewish, although I don't really believe in the religious stuff. We can still shout out the traditions. All right. Got a nice little fire here while we look at our stuff. So, how's this for a stream? Got our campfire and our robot. So, they're saying that if n's a positive integer and n is prime, that can be written as the product of prime numbers. Wait, whoa. Yeah. Wait, no, this is not a product of prime numbers, but yeah. Oh, I guess you could say that it can be written as n times 1. We don't need to include the times 1. If n is not prime, then it can be written as the product of two positive integers where a and b are both less than n. Correct. If a and b are both prime, then a or b can be written as the product of two positive integers c and d where c and d are both less than a or b. This process can be repeated until every factor of n is a prime number. Therefore, every positive integer can be written as the unique product of prime numbers. This proof shows that the fundamental theorem of arithmetic is true, and that every positive integer can be written as the unique product of prime numbers. So, I wasn't really listening to that. I was paying attention to my nice little campfire noises. I was kind of just reading through it, but they're not really proving anything. So, well, no, that kind of works. They're saying we can keep going down, but not the perfect proof. So, tell it to prove an unproven conjecture. We've tried a few of those, like Riemann hypothesis and stuff. We could try a simpler... We tried twin primes, too. So, we could think of some other good open questions, like some of the ones are number theory ones I'm not sure if it'll fully know about. Let's say prove Fermat's last theorem. That was a very complicated proof that would not fit in this place, nor would it fit in a margin. So, like I said, the fire's not going to go very long because the cardboard goes really quick, and I gave it maybe a little help with lighter fluid, but the wood's wet. So, we got a little bit of fire hanging out with us, but it's not going to go super long. Got a bunch of embers, though. Whoa, stay down, Ember. Stay down. So, they're saying that Fermat's last theorem is a mathematical theorem that states that. Okay, I'll try and. Oh, the candles are fully dead, basically. We're getting so dark. Well, I'm going to end the stream soon anyway, so we're just going to be in darkness for a minute. We got a really quick campfire. So, and someone said the Collatz conjecture. That's a good one I could put in as well. Or proving quadratic formula and stuff. And I love the chatting in the chat about different people's lives. If people ever want to chat more, the comments here are a great place, and so is the Discord for Combo Class, which is linked in the comments. And also, shout out to the people who have helped me on the Patreon. I'll be doing a shout out in a video again soon, and in some more descriptions. And let's see. They say here's a simple outline of the proof. Okay, this is not going to be right. This equation can be written as that. Okay, that could be written as, this is our integers. Yeah, they're trying to prove Fermat's last theorem in these little 5 bullet points. Lot of errors in there. Fermat's last theorem took many pages to prove. Proven by Andrew Wiles in 1993. So yeah, there's facts about 120. That'll be a good one. We're going to wrap up the stream really soon. Sorry I can't get to all of your ones, but maybe we'll do another stream like this. Maybe in my room later tonight, or maybe tomorrow or something. So, in any case, let me write, what is interesting mathematically about the number 120, and we're going to compare it to Wikipedia's one, because here we got like factorial, triangular, tetrahedral, doubly triangular, smallest number to appear 6 times in Pascal's triangle, all these types are highly composite and abundant, multiply perfect, the first tri-perfect number. Some of its factors are 360, 3 times it. It's the sum of some twin primes and da-da-da about random facts. It's called an untouchable number like we covered the other day. The sum of this the function about primes does that, or about coprimes. Yeah, coprime. They call it relatively prime, same as coprime. It's one of the only ones, factorials, that's 1 less than a square that we know. I think we only know 3 of those or something. The internal angles of a regular hexagon are all that when we use our 360-degree thing. Let's see, it's the largest integer of this sequence. You wanted to find another positive integer, Fermat, that when multiplied by any of... This interesting. Look, it's Fermat from the one we asked a minute ago, Fermat's theorem. Want to find another positive integer that when multiplied by any of the other numbers in the sequence yields a number that's 1 less... Oh, that's it. These are the Brown number pairs. That's what they're talking about. Oh, no, wait. No, this is different. Another integer that when multiplied by the other numbers in the sequence, by any of the other, yields a number 1 less than a square. And they only found this fractional number that joined the group. That's interesting. I need to look more into that fact someday. So, thank you to the people who had to go. I'm going to be going pretty soon. No worries. You can always rewatch the streams. That helps the channel too. This bonus channel literally doesn't have the right type of watch hours to even be on the partner program, even though we have more than 20 million views and hundreds of thousands of watch hours. They didn't count the ones from the shorts, and they're kind of weird with what they count from live streams. So, yeah, we still need more watch hours on like the already posted videos to even get in the partner program on this channel. So, yeah, rewatching the streams actually helps. So that's what Wikipedia says. A lot of good stuff there. Let's see what they said. It's a multiple of all these. It can be evenly divided by all those. Okay, they should have said that it's a multiple of more things than any smaller number. It's the smallest number that can be written as the sum of two squares in three different ways. Let's see. Wait, no. 120 is not 11 squared plus 1 squared. That's not true. That would be 122. This one would be 136. This one would be, let's see, 100 and, what's 36? 117, I think. So, no. This one would be 100. Exactly. 36 plus 64. I was thinking 9 squared. Sorry. So 100, this says 120 equals 122 equals 136 equals 100. Nice one there. It's sum of the bunch of triangular numbers. That's true. They should have also clarified this makes it what's known as a tetrahedral number. Sum of the degrees in a dodecagon, a 12-sided one. No. Not true. Oh, the number of degrees. Wait, what? No. The smallest number that can be written as the sum of two squares in more than one way. They already said that here. This is that phrase different, and this example's wrong. Smallest number that can be written as the product of two prime numbers in more than one way. What? And then they say it's 2 times 60 and 3 times 40. 60 and 40 are not prime numbers. Equals 5 times 24. 24 is not a prime number. And that's not the smallest number that can do that. That's the definition of like a composite number with multiple factors. This says that it's divisible by the sum of its digits. That's true. It's a divisor of the Mersenne number, which, wait, no, if that's a prime number, it can't have divisors apart from one in itself. So that's just impossible. Okay, there are many other. They got so many of those wrong. All right, we're going to try one more of these. We'll give it an easier one. What are some interesting mathematical properties about the number 6? Now, there's a lot they could say here. The number 6 it's a perfect number, highly composite, superior highly composite, triangular, factorial. So they have a lot to say about it. Hopefully. Now, sorry guys, but this might be the last one. I might wrap up after this one. Maybe restart in my room later, or maybe you do another tomorrow. It's too dark and I didn't bring any more candles. So, they say it's perfect. Wait, but this is wrong. The proper divisors of 6 are 1 and 2. And 1 plus 2 equals 3. Wait, no. They should have said 1, 2, and 3. And, okay, so they defined it wrong. So the lowest perfect number, that's true. The smallest positive integer that's not a prime number. No, not true. It's a triangular number. True. Divisible by sum of digits. Very unnecessary to state that for a 1-digit number. Highly composite, which means it has a large number. It's a much clearer term than just meaning it has a bunch. So wrong definition. It's composite. Correct. Not necessary to state that again. Smallest positive integer is both triangular and square. It's not square. Well, how are they so wrong on these? They were kind of right when I asked them, like, try and prove that square root of 2 is irrational. They were more right on that than saying, what's some cool stuff about 6? So we have to try this more later, just testing, asking it about random numbers. So that will maybe be a stream later tonight or tomorrow. Just like go through all the first 20 numbers and see what they have to say about them. In any case, thank you for joining me here. It's super dark now, but I love you guys so much. These are literally about to go out. One of them already has. So thank you all for watching. Make sure to tune in to the main channel for an episode in a day or two. And I'll have some more bonus content here soon, streams and shorts and stuff. And yeah, hope you have a wonderful night or day wherever it is. You can have fun on this thing too if you want. It was pretty easy for me to set it up. I had to just like make an account pretty quick and then I was able to do this. So have fun on that on your own if you want, or catch me do it later. Hope you learn a bunch of stuff and enjoy a bunch of stuff, and I think I'm going to log this thing off. Goodbye.